Cooperation between BCI and AI. Let's talk about the brain-computer interface, or BCI. We're going to zoom in on this one hidden signal, an automatic response that's literally hardwired into our brains, and it's about to completely change the game, not just for how we control machines with our minds, but how we might one day teach an AI just by thinking. So, how on earth does this work? Let's dive in. To really get why this is so important, we have to start here. Just for a second, imagine your mind is totally clear. You are 100% you, but you can't move, you can't speak, you can't interact with the world at all. And this isn't science fiction. For thousands of people, this is reality. And that's the harsh reality of progressive neurological conditions like ALS. It's a disease that step by step takes away a person's control over their own muscles until eventually they're fully conscious and aware, but almost completely paralyzed. Now, while it's a rare disease, the impact is just profound. As ALS progresses, a person can end up in what's called locked-in syndrome, where maybe they can just move their eyes, and in the most extreme cases, they become completely locked in, losing even that last bit of control, which cuts their final connection to the outside world. This is the exact problem that neurotechnology is racing to solve. Okay, and this is where the brain-computer interface comes into the picture. You can think of a BCI as a bridge. It's a direct communication pathway from the brain to some kind of external device, completely bypassing the body's damaged nervous system and translating what you are thinking directly into commands. So there are basically two ways to build this bridge. On one hand, you've got the non-invasive route. This uses sensors on the outside of your head, like a cap with a bunch of electrodes. It's safe, it's portable, but the scale kind of muffles the brain signals, so things can get a little noisy. On the other hand, there's the invasive path, which means surgically implanting electrodes right into the brain. Yeah, it's risky, but the signals you get are crystal clear. It's this classic trade-off, right? Safety versus signal quality. But here's the thing. No matter which method you use, there's this huge challenge. BCIs are not perfect. They make mistakes. A command to move a cursor left goes right. You try to type the letter B and a C shows up. And you can imagine how incredibly frustrating that would be. It makes the whole system almost unusable. But what if the brain itself could just tell the computer, hey, you messed up? Well, it turns out it absolutely can. Researchers have discovered that our brains have their own automatic built-in error detection system. It's this secret signal that fires off every single time we notice something has gone wrong. It's called the error-related potential, or ERP for short, and you don't have to think about it at all. It's a totally automatic reaction. The moment that BCI types the wrong letter and you notice it, your brain involuntarily sends out this tiny electrical pulse that basically screams, oops or no, that's not right. And what's so cool is you can actually see what this oops signal looks like on an EEG reading. It has this very distinct, very recognizable shape, a quick negative dip, which is that initial subconscious wait a minute moment, and that's followed immediately by a larger positive peak as you become consciously aware of the mistake. It's a unique signature that a computer can totally learn to spot. And what's incredible is just how fast this all happens. That first part, The initial dip, that's your brain's gut reaction. It happens in a fraction of a second after the error. Then, just a split second later, comes the peak. That's you consciously going, yep, that was a mistake. The whole thing is incredibly fast and super reliable. So here's the game changer. If a BCI can be trained to spot this "oops" signal, then you can create a system that knows on its own. When it's made a mistake, it becomes self-correcting. So let's just walk through what that actually looks like. With a normal BCI, an error means a slow, clunky manual correction from the user. But with an ERP-enhanced system, the whole process is seamless. The BCI makes a mistake, your brain fires off the "oops" signal, and the system catches it instantly and effectively hits undo, without you having to do anything else at all. This just creates a much smarter partnership between you and the technology. You get automatic error correction, you get instant undo actions. The system can even adapt and recalibrate itself over time to make fewer mistakes in the future. And all of this just dramatically increases reliability and, most importantly, the user's trust in it. Okay, but here's where we zoom out and things get really futuristic. What if this "oops" signal could be used for more than just fixing typos? What if you could use it to give direct feedback to an artificial intelligence? This is the core idea behind brain-AI interaction. In this kind of closed-loop system, it's not a one-way street anymore. The AI doesn't just do a command, it generates an output, a suggestion, an idea, and the BCI is watching your brain for that telltale "oops" signal. That signal becomes a direct, unspoken feedback channel. It's a conversation. This is a massive shift in thinking. We're moving way beyond simple control. Now the brain can give feedback on complex, abstract ideas generated by an AI. It's kind of like playing a game of hot or cold, right? But instead of saying anything, you're just thinking, and the AI is listening directly to your brain's evaluation to know if it's getting warmer or colder. And the ultimate goal here, and this is a quote straight from the research, is to build truly personalized AI. We are talking about an AI that doesn't just follow a set of generic rules, but actually adapts its behavior and refines its whole understanding based on the unique neural feedback of one specific person. So here's how that would work. Imagine an AI, maybe a large language model, generates a sentence. You read it, and you just silently think about it. If it's wrong or not what you wanted, boom, your brain generates an ERP. The BCI detects it, tells the AI, nope, try again. And the AI immediately refines its guess and gives you a new option, learning from that direct neural feedback loop. So this leaves us with a really fascinating question. This technology starts as a lifeline for those who've lost their voice, but it clearly points toward a future where the line between our thoughts and our machines become almost invisible, when our brains and our AIs can literally learn from each other's mistakes. What kind of collaboration, what kind of creativity is even possible?